This is video 8 in our series Analytical Mechanics. Reminder, the playlist for all the videos is featured at our website, digital-university.org. In this video, we're once again going to consider not this very simple system, but the simplest of all systems of harmonic motion. And again, it just consists of a spring, the spring constant K, attached to a block of mass M, and we imagine displacing it and then releasing it so this block slides back and forth along the x-coordinate that has no friction. And as we explained in the previous video, and as you probably heard before, that when you pull the block away so that you are extending the spring of course is going to exert a force on the block in the opposite direction, and it is like this. So the larger the displacement, the greater the restoring force, and this is the spring constant here. Or if we say x is in the positive direction, if we compress it so that x is in this direction, then the restoring force is going on the opposite direction. Okay, now force is just mass times acceleration. So let's write it like that. We have the mass of the block times acceleration. Now notice here, for this problem anyway, we're not taking into account the mass of the spring. We would do that in a future video where the spring is so massive that you can't ignore its mass. But let's put that aside for the moment. Here then, we have just this simple equation, and we can bring this over to here. So we have d squared x dt squared plus, bringing this over here and dividing it through by m, we'll have k over m times x equals 0. So, very simple second order differential equation. We should be able to solve it for x as a function of t, which means then that we can determine the position of the block along the x-axis at any time t once we solve this. It's very simple, but let's just do it formally. Typically the first step is to write the auxiliary equation, where we would say m squared plus k over m equals 0. Oh, we shouldn't use m squared here. We should use, that's going to be confusing. Let's use q in the auxiliary equation. What we're doing right now is, even though it's a very simple equation, we're doing it formally by first writing the auxiliary equation. So we'd have q squared, say, plus k over m equals 0. We're here, we have q, and the exponent on q is dependent upon the derivatives here. This is a second order derivative, so that would be q squared. If we had a dx dt in here, multiplied by say some number 3, then the auxiliary equation would look like q squared plus, from here it would be 3, that's a first order derivative, so it would be q to the first order, and that would be q to the 0 order, because that's not a derivative at all. So for this one, for this equation, where there is no dx dt term, the auxiliary equation is simply q squared plus k over m. That's not our derivative, so that's just q to the 0 power, which is 1, equals 0, or q squared equals minus km. Q squared equals minus k divided by m. So q equals plus or minus I times the square root of k over m. And we have I because here we're taking the square root of a negative number. So here, this is a second order differential equation. There has to be two solutions for x, and there is. We have x equals e to the plus I k over m times t, and there is x equals e to the minus I times the square root of k over m times t. Both of those are solutions, and if they are solutions, then any linear combination of them are also a solution to this equation. So we can write it like this: x equals, say, a, any constant, times e to the I square root of k over m times t, plus b e to the minus I, the square root of k over m times t. So each of these are a solution. Any linear combination of them is also a solution. And of course, in the previous video, we've shown that the square root of k over m is the angular frequency, omega. We'll leave it like this for the duration of our video. But this then tells us the position of the particle x, or not the particle, but the block x along the x-axis. This is telling us the position of the block along the x-axis at any time t. It's not very useful to leave it in this form, and this now is where we get into, where we employ Euler's relation. Not Euler's equation like we derived in our second video, but Euler's relations, which are these. E to the plus I theta is the cosine of theta plus I times the sine of theta. And if we have e to the minus I theta, then in here we replace theta with minus theta. But the cosine is an even function, so the cosine of minus theta is also the cosine of plus theta. Here we replace theta with minus theta, and the sine is an odd function, so this would be minus the sine of theta. Now, x we had written like this. So here then, here we have plus I, the square root of k over m times t, multiplied by a. So we're going to use this relationship here. So this turns into this, a times the cosine of this, plus I times a times the sine of this, right, according to that equation. And then here we have minus I times the sine of theta. Right here, that gives us this relation. Here's minus I times the square root of k over m times t, and this is multiplied by b. So that's going to be the form of this equation. B, then we have the cosine square root of k over m times t, minus I times b times the sine of the square root of k over m times t. And then we can collect terms here. We'll have the cosine here times a plus b, and then we'll have the sine of I times a minus b. So that's our equation then for the position of the block along the x-axis at any time t in terms of trig functions. Problem with it in this form is it's a complex function because we still have I of course being the square root of -1. So let's work with this equation. Remember now, this equation that we have came from solving this rather simple looking second order differential equation. We're going to erase all of this now and write in the solution that we have, at least the form that it's in right now. So we have, get rid of all of this, and the way it stands right now is the position of the block along this x-axis equals a plus b. Remember, an a and b were any arbitrary constants times the cosine of the square root of k over m times t. Then we had plus I times a minus b times the sine of the square root of k over m times t. And this gives us then the position of the block anywhere along the x-axis here as it's sliding back and forth at a particular time t. This is a complex function the way it is right now. Well, the a's and b's are arbitrary constants, so let's choose, first step, let's do it like this. Step 1, what if we have a equals 1/2 and b equals 1/2? A minus b, that term is going to be 0. A plus b, that's going to be 1. So we can say x equals the cosine of the square root of k over m times t. That's one solution. What if we chose our constants in a different way? Say, let a, suppose that's equal to, say, minus 1/2 times I. And we say, let b equal plus 1/2 times I. Now here's our equation for x. We have a plus b. That plus that will be 0. Then over here we have I times a minus b. So we have minus 1/2 I, that's a, minus b, that's this, 1/2 I. And this will equal I times negative 1/2 minus 1/2 is negative 1. So we have minus I. I squared is negative 1 times minus 1. So when we choose these values for arbitrary constants, we get x equals, this is just 1 times, again, a and b are equal to these specific values now. We can choose anything we want because these are arbitrary constants. So here, when we chose a is minus 1/2 I and b is plus 1/2 I, that term is 0. This becomes 1. So x equals just this. The sine, the square root of k over m times t. So we say that's a solution, and we say this is a solution. So if that's true, then any linear combination of these should also be a solution. So we have then x can equal any arbitrary constant times this, call it C1, times the sine, the square root of k over m, times t, plus C2 times this, the cosine, square root of k over m, times t. Again, this is a solution, and so is this, and if they are, then any linear combination of them will also be a solution. So now we have the position of the block at any time t in terms of trig functions, and there's no more I in here, so this is a real function. It's not a complex function. So this is what we get now for the position of the block at any time t. Well, if you watch video 6, we also derived an equation for the position of the block at any time t, and what we obtained in there was x equals, that was the amplitude, times the sine of the square root of k over m times t plus some constant. And we discussed how this constant is a phase angle, and its value depends upon really the initial conditions of the problem, and it gives the position of the block at time t equals 0. Again, we discussed that in the previous video. But right now what we want to show is that this is an equation for the block at any time t, and so is this. This one we derived in the last video, video number 7, and that ultimately stemmed from an energy consideration of our system. This was from Newton's law and just solving a really simple second order differential equation, but they look like two entirely different kind of solutions here. So let's see if there's a way that we can reconcile this. So we're going to write these two at the top and get rid of this stuff now. So what we just derived, x is equal to, and we had some arbitrary constant times the sine, the square root of k over m, times t, plus a different arbitrary constant multiplied by the cosine of the square root of k over m. Multiplied by the time. And that is much different than this equation that we derived in the previous video. So let's look at this in more detail. Again now, these constants C1 and C2, they can be completely arbitrary. So since they're arbitrary, let's choose them like this. The amplitude the motion, that's A. So let's set it up. We want, and it's our choice if we want to, since these are arbitrary. Let's set it up so that the amplitude A multiplied by some other constant, we'll call it C1 prime, is what this is. And likewise, the amplitude A multiplied by some other constant equals this one. Remember, these are completely arbitrary. They can be anything we want. So for this and this, for C1 prime and C2 prime, let's have them so that they're less than or equal to 1 and greater than 0. Which means we're setting this up then so that C1 is either going to be as large as A or some fraction of A. And likewise for C2. And that's completely legitimate because these are totally arbitrary. So these are one of the choices that we want to make. So if we do that, let's take it a step further. C1 and C2 are between 0 and 1. Well, C1 prime. So let's say that let C1 prime equal the cosine of, say, C. And C2 prime, that will equal the sine of C. And by doing that, this then is always going to be larger than 0 and greater than 1. Same here. Okay, now, if we do that, all we're doing is just fiddling around with these arbitrary constants. But if we play this game, where does it lead us? Well, we have here x equals C1. But C1 is this, A times C1 prime, and C1 prime is this. So, in fact, let's just clarify this. C1 equals A times the cosine of C. The way that we're manipulating these arbitrary constants. And C2, that is equal to A times C2 prime. That's going to be A times the sine of C. Now, after we monkeyed around with these arbitrary constants, let's rewrite the equation for x. X equals C1, that's this, times this. So we're going to have A times this, the sine of the square root of k over m times t times the cosine of c. A times the cosine of c is c1, and that's what that is. Again, all we're doing now is just fiddling around with these arbitrary constants. Then we have plus c2. Well, c2 is A times the sine of c. So we're going to have A times this, the cosine of square root of k over m times t, and then we'll have the sine of c. Get this into better focus. Okay, again, A times the sine of c, that's right here, that is c1 right here. So here we have this part. C2, that is A times the sine of c. A times the sine of c. And then we have the cosine right here. And the reason why we did all that fiddling around is, look how this turns out. We have sine, cosine, plus cosine, sine. So this will equal, factor the a out, and we will have sine times the square root of k over m times t plus c. Expand this out and you get this. So what we have shown then is that this equation which is the same as this one after we fiddled around with these arbitrary constants, that we get this. So that indeed the results are consistent when we have x written like this, or when we have x written like this. Now let's just look at one more aspect of this very quickly. To try to clarify something else. So we have x equals a times the sine square root of k over m times t plus c. And that's what we derived in the previous video. Now, we also said this, that when we were fiddling around with these arbitrary constants, we had it set up so that a times the cosine of c was c1, a times the sine of c was c2, so a is going to equal the square root of c1 squared plus c2 squared. So we can have it like this triangle here. That's the angle C, C2, C1, sum them up, take the square root, that's A. So that A times the sine of C is C2, A times the cosine of C is C1. So that means, now remember before we said C, which is this now, we said in the previous video that that was an arbitrary phase angle. You can see it coming into play right here. We can say, well, that phase angle is equal to the inverse tangent of C2 divided by C1. So when we solve Newton's equation, we get the second order differential equation, and we get it in this form. We can say, yes, there's a phase angle, and that phase angle will equal the inverse tangent of C2 divided by C1. Now, as you saw in the last video, the initial conditions might be set up so that this is 0. And if that's true, what that means then is one of these arbitrary constants will come out to equal 0 when you set up the initial conditions. Okay, that's all I want to say in this video. We just want to show that even for a very simple system, it can get to be complicated. And when you solve it in different ways, like for example, here we're solving for the position of the block, as we did in the previous video, and then here we did it a different way, and initially it seemed like we had entirely different answers, but in fact they are equivalent, and this phase angle can also be obtained from this expression as well. Okay, that's it for this video. I'll come back and join us for the next video, and we're going to start to consider some more complicated situations.